Hello, I'm Riccardo Rattazzi, and I will briefly tell you about particle physics and the training offered by my group. Particle physics is called so, but is actually about the fundamental laws of physics. This connection is made evident by the fact that particle physics can be viewed as the unavoidable consequences of the two pillars of modern physics, relativity and quantum mechanics. According to relativity, there cannot exist instantaneous action at a distance. Two bodies at different points in space can only interact via the exchange, if you want, of waves in a field that permeates all of space. So relativity implies the existence of fields with their waves. What about quantum mechanics? Well, quantum mechanics has several implications, but one universal implication of quantum mechanics is the discrete nature of the quantities that you can measure in the micro world. In particular, the waves that are needed because of relativity will have to have a discrete intensity if you can measure them precisely enough. And as such, there will exist a wave of minimal intensity. Okay. What is this wave? Well, this is just a particle. Okay. So this is a qualitative way to see the connection between these basic principles and particle physics. More formally, the encapsulation of these principles into physics is done by quantum field theory. Quantum field theory is a mathematical construction that encapsulates the principles of relativity and quantum mechanics. So what does quantum field theory do? Quantum field theory explains the existence of particles and dictates the structure of their interaction. The standard model is just a specific quantum field theory that describes basically all that we see in the physical reality that surrounds us, basically, I say. Okay. So the standard model describes the existence of matter, okay, quarks, leptons, particularly the electron. It describes the forces we see in nature. Okay. So these forces are the electromagnetic, the weak, the strong, gravity, and the Higgs force. Okay. It also describes the nature of this force, in particular, the geometric nature of this first four forces, okay, and also the non-geometric nature of the Higgs force. And the non-geometric nature of the Higgs force, I don't have time to tell you, is also part of the open questions. Okay. So the description of physics offered by the standard model and by quantum field theory, it's very mathematical, very accurate in a sense. And in fact, the standard model is the most precisely tested theory in science. Okay, so for instance, some of the predictions of the standard model, the one that concern the electron gyromagnetic ratio, are tested with 1 part per billion precision. Okay, there's no other prediction in any field of science that has this precision. And it's also important to point out the breadth of the encompassed by particle physics. In a sense, within the picture offered by particle physics, atomic and nuclear physics are just complex corollaries of these basic principles of relativity and quantum mechanics. Anyway, in spite of this success of quantum field theory and the standard model, big mysteries persist, and this is what makes this field interesting. And these have been even made deeper recently by the Higgs discovery, recently in the last 10 years. Let me just list some of these mysteries. One is the origin of the matter-antimatter asymmetry. Why are we made of just matter? Why aren't there other guys made of antimatter somewhere else? What is dark matter made of? Okay, we know there exists a type of matter that is not accounted for by the standard model. So these are very concrete questions that basically everybody can understand. But actually, the biggest question about the standard model are more subtle and have more to do with the nature, with the genuine quantum nature of quantum field theory. And they can be subsumed in terms of the incredible properties of the vacuum. Let me briefly explain that. Okay. So classically, the vacuum is where nothing happens. So if like in a harmonic oscillator, the vacuum is the state of minimal energy where the particle is at rest at the bottom of the potential. But as you know, the ground state in quantum mechanics is always jiggling. So there's always some motion even in the ground state. And that is the case also in quantum field theory. In quantum field theory, the vacuum where there's no particle around is a very active place. And here I'm just depicting this quantum fluctuation popping out of the vacuum. Okay, and this quantum fluctuation are fluctuations in energy, particles formed, being destroyed. It's something going on continuously. Now, this happens at all length scales. And because of this, there are some specific important quantity in physics that cannot be computed, that simply cannot be computed per se in the standard model. And this pertain the range of the Higgs force. One of them pertains the range of the Higgs force, and the other pertains nothing less than the size of the universe, okay? And while these things are not calculable in the standard model, we can think of reasonable extensions where they are calculable. And whenever, and in any extension we can think of, we expect the result of the result which is given by this computation is way, way off with respect to what we observe. For instance, from this computation, we would expect the Higgs force to be confined over a distance of 10 to the minus 30 centimeters, which is about 15 orders of magnitude less than where we observe it. Okay, back 16. Similarly, the universe, the size of the universe is suggested by these computations, which are the basis, I mean, which are just what we can do at the moment, should be less than 10 to the minus 4 centimeters. This is much smaller than ourselves. So we can, this totally doesn't make any sense. Well, these are, there is a catch here. This is so unless, and we see it in the computation, some fundamental parameters are tuned to some insane accuracy. So it's clear that there is something we are missing, okay? And what is that we are missing is not clear, okay? We have ideas, but it's not clear, okay? And partial answers may come from the exploration of the Fermi scale at the Large Hadron Collider or future machines, but it's my feeling that deeper answer will probably only come from a radical deformulation of basic principles, okay? Perhaps aided by other experiments, not yet clear which ones. All that I want to tell you is that quantum field theory and particle physics are a very precise and very successful branch of science. And at the same time, but they're also a branch where there are huge failures. In other words, the excitement of this field has to do with the fact that there is, at the same time, big questions, big puzzle, big mysteries, and big successes. And it is this combination that makes it an exciting field. Now, beside that, there is still a lot to learn in this area. So this is, even whatever will come next will have its basis in quantum field theory. Okay, and here I'm giving you some example. If you, I will give you this keynote presentation where you can look at my recent or less recent work to get an idea of what I'm doing. Okay. So let me come with the notion of the TP. The TP, let me present here the training that we offer based on the first 3 semesters, okay? The first semester is the master project. So the first semester of TP is, I mean, we view the TP as a complement to what is done in the courses, in the master courses, because this discipline requires a very broad and very deep knowledge, and the master courses cannot offer that. I mean, they do offer a lot, but there's not enough. And so this is the way it's organized. For example, in the first semester, we normally give a training in the basics, okay? And the basics is symmetry and particle physics, okay? So as you say, relativity, which is the basis of quantum field theory, has to do with symmetries. So again, so this is what we do. Group, selection rules, space-time symmetry. There is going to be exercises every week, a lot of exercising and presentations every Monday. Okay, the students come and present the exercises that they're trying to solve, if they solve them, and the assistant will help them out with that. Okay. And at the end, there's going to be a little project that can be on some, even on some advanced subject like identification, quark model, supersymmetry. The second semester is more about quantum field theory. Okay, there you already know the basis of quantum field theory from QFT1 and part of QFT2, the classes. So there will be more about S matrix, Feynman diagram, the computation of fundamental process. At the end, the project will be slightly bigger, a less little project, and it could concern the standard model and some of the open problems. Particularly, it could concern some of the questions that came up recently in some of the data. For instance, there is, if some of you may have heard, a recent measurement of the mass of the W boson seems way off from the prediction of the standard model. The question is, what does this mean? Okay, and in order to answer this question, there is a lot of theoretical work that needs to be done. So this is not, yeah, this is a hard question. Okay, so that's an example of a project. The project could just represent the first steps towards addressing this question. And then there is the third semester where we give, our aim here is to give in the Landau style, the style of the Landau school, a very robust and very solid training in quantum field theory. So there's going to be mostly advanced quantum field theory, the standard model done in a deep way, and also some advanced subject like conformal field theory and gravity. And then beside the preparation for master project. So prerequisites, well, they're here, okay, suggested. I mean, yeah, this is all, I mean, the broader your horizon, the better. That's it. So I'm gonna, my goal is to have at most 3, maybe 4 TP students. I always end up getting more, but I think it's time that I take fewer because it's very hard to deal with more than 3 or 4. I mean, it's very, very difficult. The bottleneck is the master project. Okay? So this is going to be my group next fall. Okay, it's going to be me. It's going to be Tim Cohen, who is going to arrive in the summer. He is part of a joint program we have with CERN. He's going to be here for a few years. Okay, so he's already a senior scientist. Okay, and then there's going to be 3 postdocs. Okay, here and 2 PhD students. Okay. Thank you very much. I'll be happy to answer any question you may have. Just send me emails. Bye-bye.